Activity 2.2.1, product analysis, starts our journey in looking at how things are manufactured, right? So we need to look at materials, and need to look at how something is actually put together. So we start off with a project where we sort of reverse engineer a product, right? So in this activity, the students need to find some sort of object or something from home that they can bring in that they can actually take apart. And more than likely, I'm guessing, probably not going to go back together. So it's important that they find stuff that isn't of value to them. All right. So you have them come into groups, have them take apart those objects, and then they're going to start to choose different parts from those objects in order to analyze. When I end up going through this, we ask that each student chooses a different material. So if we know something is plastic or wood or metal, so we're looking at these different categories of materials. So they want them to sketch or design. If your students are really good at using Inventor, they can draw it up in Inventor. That helps us later when we're trying to figure out maybe the volume of the part or something to that effect. So they have them sketch things out in their engineer's notebook. They make a list of the parts and pieces. But the idea here, basically, it's like we take this product, whatever it might be, and we pull it apart. So in this case, maybe a student takes this rubber suction cup material here, and another student takes this plastic part here, or maybe they use like one of these brackets or metal screws. But when they do grab the material, it should be one solid material. So grabbing the circuit board here is not going to work well for us. So they choose that product. We run it through a system of tests or a series of tests. So a continuity test, you can use your multimeter for this just to see if it's electrically conductive. Does it have iron? Is it a ferrous metal? One of the easiest ways to tell if it has iron is if it's magnetic. Not necessarily all metals that contain iron are magnetic, but this one, if it's heavy in that, it definitely will be magnetic. We can test the hardness. Usually we use a nail. We see if we can scratch it. And when we do scratch it, if it does it chip or flake off? Does it just like kind of mash? Nothing really comes off it. So we can kind of tell, is it a softer material or a harder material based off of that result. We mass it, so we put it on a scale, and we see what its mass is. We measure it to figure out what its volume is. And then that's the actual density of the material down here is probably one of the most important things for us, because if they do all this correct, what they can do is go out and to charts. Like let's say it's a plastic, there are specific density charts for plastics to figure out what type of density is. Once we figure out, or excuse me, what type of plastic it is based off its density, and as soon as we figure that out, then we can look at other information to see, okay, well, these types of plastics are typically used for whatever it might be, and then it might help us to figure out what it is. So they also get into looking at surface area, and is it ability to bend and deform? Is it malleable? Is it something that when we bend it, it breaks? They repeat the process again, going through all of those different tests for a couple of different parts. Okay. And in the end, what we're trying to do is figure out what the material is based off of that stuff. So before I'd have them go through and pull everything apart, there is a presentation introduction materials that we would go through. So one of the places that the students can go to find information is this website called MatWeb. So underneath MatWeb, there's a lot of companies that sponsor this, but you can go through there and you can search for maybe steel, and it's going to give you a lot of results because there's lots of different types of steels, and or like Morgan, there's different types, different companies that use different specs for these different metals. So they might go through and think it's a certain type of steel, and then they can see, okay, look at this. There's a bunch of different series of steel. Let's click on those, and let's see if it matches our density, or let's see if it matches our hardness tests, that type of stuff. So it's getting them into this kind of like analyzing the material mentality. Then we talk about material history. We talk about how periods in time are actually defined by the materials that they use, like the Stone Age or the Bronze Age. And one of the questions I always ask them is, okay, so we had the Stone Age, now it's the Bronze Age. Did we run out of stones? Well, it's not that we ran out of stones, it's just that we found a better material, a material that suited our need and ended up working better for us. We still use stones, but not necessarily for all the things that we used it for before. So our technology, science, and material advancements are all based off of each other. If this was an animation, it would show that if my technology improved, then I have the ability to do different science or material testing. If the materials improve, then I have the ability to improve my technology. So they're all interrelated as far as how we improve in our materials. So different composition, we have elements. We know that in our charts, we have categories, metals, nonmetals, and metalloids. We can look at metals, and we know that for the most part, most metals are dense. They're typically shiny. There's luster, is something reflective. We know that they're great conductors, whether it be heat or electrical energy. They're relatively good conductors. Again, this is a generalization. Our non-metals don't necessarily share the same principles as the metals do. We don't think of them as these heavy, dense things, but non-metals could be gases or things that are not electrically conductive. They tend to not be malleable and flexible, but they tend to be more brittle and stuff that breaks easily. And then we have that crossover where they share different characteristics from both metals and non-metals. We get into things like mixtures and compounds. Well, compounds where we're combining different materials, different substances in order to get an end result that suits our need. So maybe aluminum is a great product because it's light, but it's not necessarily strong enough for us to do what we want to use it for. So we're able to do different compounds or alloys or different ways of making that material better for us. So again, the age-old discussion of compounds versus mixtures. Can we take them apart in the end, or have they chemically been changed? So I want the students to be able to know these different categories. I know in the past in the EOC, we've had different questions that had them categorize these materials, and based off of the different types of materials, select which path you would go for a certain product or certain design. So it is important that they know them and they can place specific materials within them. So that goes through this presentation where they talk about the different types of materials. Metals, pretty easy. You can go around the room. Students can touch the legs on their chair. They can say what they feel, what they think about when they think about metal. Ceramics might be a little bit difficult. You know, a lot of times we talk about ceramics, we're talking about stuff like toiletry, you know, your sinks and things like that. A lot of people think of your dishes. But one of the really cool ceramics is our space shuttle tiles and how good they are at being able to handle energy. So one of the things that's a cool video to show them is if you go out to YouTube, you can search for the space shuttle tiles, and they actually do a demonstration here where they put a space shuttle tile into the oven, and they pull it out, and it's literally glowing orange. And within seconds, somebody's picking it up. Now you can see kind of like the edge there is actually kind of gray because it's dissipating that energy very quickly. And they're able to pick that thing up after it's heated up to several thousand degrees. One of the reasons why we use the space shuttle tiles. So that's a good one. It's kind of fascinating. We do use ceramics in our resistors and capacitors and things like that. We know that organic materials, carbon-based, you know, things that we're growing, living type of things, they're good because we can get them back, we can grow them again, but they have problems. Maybe they're not quite as strong as something that we need. Polymers, we get into plastics and elastomers. Most students are, you know, understand what plastics are. Elastomers like a rubber band. They might not be able to identify thermoplastic versus thermoset. You know, why do we have thermoplastics and why do we have thermoset plastics? What are the benefits to these things? So I do like to talk about the vulcanization because you think about this rubber material, which is like a rubber band, which students know they can stretch back and forth quite easily. But what ends up happening over time is it breaks. It's not very durable, right? It's not something that you can really wear. But then you say, okay, well, your tires in your car, that's an elastomer. That's a rubber material. So how does that last? How does some of those tires last for 40, 50, 60,000 miles on something that's rough like pavement? And it's this process of vulcanization where we take something that is rubbery in material and we make it not only flexible but also strong and more durable. And we talk about the vulcanization process. Charles Goodyear was a big part of that, starting that process, how to take that hardened rubber and make it more flexible and durable. And obviously it's evolved over the years. We get into these composite materials where now we're combining two materials to get a better result. Fiberglass boats. They combine plastics and fiberglass ceramics, that type of stuff. Carbon fiber, you know, different ways of making something really, really strong, but also flexible. So why would we choose different materials is kind of the next thing. We've been talking about this the whole time, but then we get into actual material selection, material type terminology. So mechanical properties, thermal properties, and so forth. So when we get into actual testing, we look at its strength. So whether we can pull it really hard or we can twist it or we can squish it depending on which direction we need it to be. So that's our hardness or ductility. Like wire is great, metal is great. We can really stretch it out really, really, really long before it wants to break. So they go through and we look at some of these different properties. At this point, we've already talked about stuff like thermal capacity, thermal conductivity, so our CP or our K values here. We even kind of alluded into thermal expansion. When you heat something up, it wants to move on us, right? It wants to expand, and then we cool it down, it shrinks a little bit. That's something that's important for design. So we know if there's too much thermal expansion, it might not work. We get into our electrical properties again, reviewing some of the stuff we've already talked about back in Unit 1. And then looking at different chemical properties, depending on what we're using it for. Is it a food grade material? Can we use this material in order to make our product? And then get into talking about different material selection in the future. So fullerenes, which is not necessarily a new thing, but we haven't really maximized the use of these little Buckminster buckyballs that they would call them. So this different shape that we get out of carbon, which can be, when we can combine them, super, super strong. We just haven't come up with a really easy and fast way of creating them and using them. Liquid crystals, biocompatible materials, just looking at prosthetics and hip replacement, stuff that's going to live inside of your body without it hurting you or damaging something else. So material selection, presentation, pretty important. The students use that knowledge in order to go through this activity 221 in order to figure out what materials they have based off of the materials, the properties of those materials.